Hi everyone and welcome back to my channel A in Economist. So this is going to be a continuation of my previous video of autocorrelation. In the previous video, if you remember, I have explained the concept of autocorrelation and I have also pointed out some of the consequences of autocorrelation if it is present in our linear regression model, right? So this is going to be a continuation of that video, and in this small video, I'll be discussing some of the consequences. Specifically, I will be mathematically deriving the consequences, right? So we'll see why under autocorrelation the estimators are still unbiased, why they are inefficient, and how to find that out, right? So let's start with lecture number 16. So consequence of autocorrelation. So let us consider the model. Let us consider our model in this particular form. Suppose yt equals to beta xt plus some error term, say u. Right? I haven't included the intercept term in the model, but even if you include, the results will be absolutely same. So you can consider it as your homework, that include the intercept term and derive the same thing that I am deriving in this video, right? So now where ut has a particular form, this is rho ut minus 1 plus et, where t will be from 1 to up to capital T, and also mod value of rho is less than 1, right? So this is the general structure of our model. See what I have done. I have taken this linear regression model. Xt is the only explanatory variable here, and now this error term ut suffers from autocorrelation, which means that, see, this is the autocorrelation. This is how you introduce autocorrelation in your model, and this is the first order autocorrelation. See, first order autocorrelation means the maximum lag value that you have in your model is 1, right? This is the maximum lag value. So if it is ut minus k, then it will be kth order lag value or kth order autocorrelation. But it is the first order. Here you have the first order because the maximum lag value that this error term can take is 1, right? I hope this much is clear. And this mod rho is less than 1. This assumption is very important. If you have seen my time series video, I have said that when mod value, this coefficient value is less than 1, then the series basically converges. Now this model is a convergent and stationary model basically, right? This model is weakly stationary, and so this weak stationarity assumption has to follow in this particular case also, right? So this basically means that minus 1 less than rho less than 1. Rho lies between minus 1 to plus, right? I hope this much is absolutely clear. Now what will you do? You will use a recursive relation. So from here, what you can write about ut minus 1? It will be simply rho ut minus 2 plus e t minus 1, right? And what will be ut minus 2? It will be rho ut minus 1 plus e t minus 2. So in this fashion, these things will follow. Now understand one more thing here, that please differentiate between et and ut. See, ut is the error term in our original model that suffers from autocorrelation, right? This ut suffers from autocorrelation, but et does not suffer. Et is independent and et follows all the other CLRM assumption. Expectation of et is 0. Variance of et is some constant, which is sigma e square, and so on, right? So all the assumptions of CLRM will hold in this et, but in case of ut, the autocorrelation assumption is getting validated, right? So this distinction is very important. Now what you can write from here is that you can write ut in terms of the recursive form that you have derived. So see, ut is rho ut minus 1. Instead of rho ut minus 1, replace this particular thing. So you will have rho, then ut, rho, and then ut minus 2 plus e t minus 1 plus et. So this will give you rho square ut minus 2 plus rho et minus 1 plus et. Right, again you can substitute this particular thing if you do. Let me do one more step. Rho ut minus 3 plus et minus 2 plus rho et minus 1 plus et, right? So if you simplify, it will be rho cube et minus 3 plus rho square et minus 2 plus rho et minus 1 and et. So ut takes this particular form and this process continues. You can, use this thing as many times as you want. But for our purposes, what we can say, if we continue this substitution, process for r periods, suppose, where r goes to infinity, r is very large basically, r goes to infinity means r is very large. Then what will happen? Then see what you can write. You can write this rho to the power r ut minus r plus there will be multiple terms, and in the end you will have rho square et minus 2 plus rho et minus 1 plus, right? So what I have done, simply see this recursive relation. From this particular recursive relation, you will understand what will be the rth time period case, right? So see here for the second, when you are doing the second iteration, first term is rho square ut minus 2. So if you are doing it for r times, it will be rho to the power r ut minus r, and there will be many more terms in the middle, and the final terms will be same as this, right? Same as this particular thing. These terms will always be there, right? So this is the structure, general structure of ut when r tends to infinity. Now, can you pause this video and guess when r tends to infinity, what will be this rho to the power r, this particular term going towards? So you can pause your video and think what will be this value. This value is simply going towards 0, right? Why this is so? Because rho lies between -1 and +1. So that is the importance of the assumption that we have written previously, right? So when I define the model, I said this thing is very important. When this autoregressive function is convergent or is weakly stationary, then only this relationship holds, right? So this assumption is very important. Why this is so? See, rho lies between -1 to +1. Suppose rho is half. So if you do half to the power r, when r goes to infinity, then what will happen? 1 by 2 to the power r as r goes to infinity, and this will be 0, right? So if this part is 0, then the entire thing is 0. So ultimately, this portion is going towards 0. So for r going towards 0, what we can say, ut will be simply the rest of the portion. So you can write it in the inverse fashion. So write this term first, and then this term second, this term third. If you do that, it will be et plus rho et minus 1 plus rho square et minus 2 plus so on and so forth. It will be infinite number of terms, right? So this is what we will get. Now the process becomes very simple. Simply take the expectation on this. So expectation of ut will be simply expectation on each of these individual terms. So it will be expectation of et plus rho expectation of et minus 1 plus rho square expectation of et minus 2, so on and so forth. Now, again, as I have told you, et does not suffer from autocorrelation. Autocorrelation applies on ut, right? This distinction is important. So what will be this? Simply 0. It will follow the CLRM assumption. Again, rho into it will be 0. Again, rho square into 0. So entire thing will be 0. And the reasoning is simple, that expectation of et is 0 for all t, right? So under autocorrelation, expectation of ut is still 0, right? What we have found out, expectation of ut. This is expectation of ut is still 0 under autocorrelation. Under autocorrelation, expectation of ut is still 0, right? This is the first result. Now, how do you find out the variance? Let me do it. Variance of ut. Let us do this. Variance will be simply expect et plus rho et minus 1 plus rho square et minus 2 plus so on and so forth. Take variance individually, variance of et plus this will be rho square, variance of this is e basically, et minus 1 plus rho to the power 4, variance of et minus 2, so on and so forth, right? Now, what will be variance of ET? As I have told you, again, this follows the CLRM assumption, so it will be a constant. ET is homoscedastic, basically. UT, we don't know, but ET is homoscedastic, so this will be simply sigma E square. This is a constant. Then rho square, sigma E square. Rho to the power 4, sigma E square, and so on and so forth. And then what you can do, you can take this out, 1 plus rho square plus rho to the power 4, so on and so forth. Now this can be solved using a GP series formula, infinite sum of GP series. So it will be simply 1 by 1 minus rho square, right? This will be what? We will get variance of UT. This is variance of UT. Now notice one thing, that if you put rho equals to 0, if you put rho equals to 0 in this expression, what will you get? Variance of UT will simply be sigma E square, and then it will be homoscedastic, right? Variance of this will be, sorry, not homoscedastic, it will be not suffering from autocorrelation. Sorry for that. See, this rho, what is the importance of rho here? This expression is sigma E square upon 1 minus rho square. Now, where have we introduced this rho term? Let me go back. See, if this rho is 0 here, this is the relationship. This is where we introduce this rho. So if this rho is 0, what will happen? UT will be simply equals to UT, right? This entire thing would have been 0 if rho is 0. So this autocorrelation term will not be introduced in the model if the rho is 0. So this is the parameter which introduces, rho is simply the parameter which introduces autocorrelation in our model, right? So if you put rho equals to 0, UT and ET will be exactly the same, and there will be no autocorrelation, no heteroscedasticity in our model, because ET follows the CLRM assumption, right? So if this rho is 0, variance of UT will simply be sigma square, and there is no autocorrelation in the model, and the model will be exactly just like CLRM. So for our assumption, what we need is that rho should not be equals to 0, right? If the rho is 0, then there is no autocorrelation. Then there is no autocorrelation in the model. If rho is not equals to 0, then autocorrelation is introduced, and this will be the variance of the error term. So what we got is that the expectation of the error term is 0. Expectation of the error term is 0, just like CLRM under autocorrelation, but the variance that we get is something like this, sigma E square 1 minus rho square. Now this we have done for the error term. We haven't gone into the estimators expectation and variance. When we talk about unbiasedness and efficiency, we talk about the estimators expectation and variance, right? So let us do that. So let us start with the model again. So model is this, yt is beta xt plus ut. So this is our model. Now if you apply OLS, what we will get as beta cap? Under autocorrelation also, this will be simply summation t xt ut upon summation xt square. This is the formula. This is the same as we have done multiple times before. I am not deriving this thing. In exams, if you want to use this expression, you have to derive this. I am not doing this because I have done it multiple times before. So this is the same. Now what you can do simply, let me do it here. Instead of ut, write, oh, sorry for that. This is xt, yt. So in the numerator, you have covariance of xy upon variance of x, right? So this will be yt, sorry for that. Beta xt plus ut. So you are just replacing this yt by this, and this will be t square. So summation t, this xt square will cancel out, beta will come out, plus you have summation xt ut upon summation xt square, right? This is what you will have. So what you can do from now is that this and this will cancel out. So you will be left with beta plus summation xt ut upon xt square, summation xt square. And this will be beta cap auto. Now what do you do? Simply take expectations, right? Simply take expectation on both sides. So expectation of beta cap auto. So see, this is a fixed parameter. Expectation of beta is simply beta. So write beta here and then summation t xt, and expectation will be on ut upon summation t xt square. So expectation of beta cap auto, this will be simply beta, since expectation of ut, as we have found out, is 0. Right? This has to be proved in the exam. This is the same thing that I have proved here. Right? This particular thing, that expectation of ut is 0 even under autocorrelation. Right? So this entire thing has to be shown, and then only you can derive the expectation. So what you have shown here is that unbiasedness property holds. Right? This means under autocorrelation, beta cap is still unbiased estimator for beta, right? This is what we have. Now the final thing that we want to show, that this estimator is inefficient, which means the variance is not the same as the variance that we have obtained in the OLS case or CLRM case, right? So blue property will not hold. How to show that? For that, we have to find out variance of beta cap auto, right? Find out the variance. What is the formula for that? The same formula as we have used multiple times, but it will be only applicable for beta cap auto, basically, or under autocorrelation. So expectation of beta cap auto. This is the formula, right? Expectation of beta cap auto minus expectation of beta cap auto whole square. So this will be expectation beta cap auto minus, we have just shown that this particular thing is simply equals to beta cap, sorry, beta, this we have just shown because it is unbiased. So you can replace this beta here and take square. So expectation of, now see what is this particular thing. This can be shown from here. Expectation of beta cap minus beta is this particular thing, or go back to this, use this particular expression. If you take this minus here, you will be left with only this, right? Summation xt ut upon summation xt square. So ut xt upon summation xt square and a whole square of that. Now what you can do, you can expand it. So summation ut square xt square plus 2 summation. If you put here 2, then double summation is not required. Otherwise, you have to put double summation. ut minus s xt xt minus s, right? And then what do you have? You have summation xt square here as it is, and a whole square of that. So now let me go to the next page. So it will be what? Variance of beta cap auto. See, the initial will be xt square will come out and variance will be on, sorry, not variance, the expectation basically. Expectation will be on ut only. So expectation of ut square plus 2, then summation xt minus s, and then again expectation will be on ut minus s, right? Summation upon summation xt square and a whole square of that. So what you can say, beta cap auto is this will be what? Expectation of ut square. This summation xt square upon summation xt square and a whole square of that plus 2 summation xt minus s expectation of ut minus s upon summation xt square whole square, right? So basically what we get here is this will be simply sigma square upon summation xp square plus some this particular thing. Now see, this thing is not equals to 0 now. Under autocorrelation, this particular thing is not 0 and this particular thing cannot be, further, solved. If you try to solve this, it will be a very messy expression. But what we can know here is that this will be some positive term. This is not equals to 0. This is xt and xt minus s. We can assume they are positive and this is the whole square of some terms. Whole square and then again whole square. So this whole square term is always greater equals to 0 and the numerator can also be considered as greater equals to 0 and it is multiplied by a positive scalar too. So this plus some positive term, right? Plus some positive term. So this will be the variance and you can try to solve this in in a much elaborate way, but this will not deep anything because this is the only expression that you need to infer anything. So what you can do from here is that can you identify what is this? Can you identify what is this particular expression? If you remember, this is simply variance of beta cap, what we have got under blue, right? What we have got, this is sigma square upon xt square, which is something that we have derived in our CLRM case, in usual CLRM case, right? Under, not under any sort of violations, right? So what we see here is that our variance under autocorrelation, variance of beta cap under autocorrelation is simply variance of beta cap under the blue property, what we have got under CLRM plus some positive term, right? Plus some positive term. So what we can infer from that here is variance of beta cap auto is strictly greater than variance of beta cap under blue, right? So this is what we wanted to show and which basically means that variance of beta cap auto is not the minimum variance. Why this is so? Because if you remember in the Gauss-Markov theorem, we have said that variance of beta cap blue is the least, right? Under CLRM assumption, the OLS estimators gives the least variance, right? They are unbiased and they give the least variance. So this particular variance is the least. So since we got that variance of beta cap auto is strictly greater than variance of beta cap blue, we can say that variance of beta cap auto is not the minimum variance, which means that the estimator is inefficient, right? This is the definition of inefficiency. Inefficiency means the minimum variance cannot be attained, right? And this is how you prove the entire thing. So this is all from my side for today. Let me give you a quick recap of whatever we have done here. So in autocorrelation, we have in the previous video already explained the concept and the other consequences. The only thing left was to show, to derive everything numerically or, using this model. So in the consequence, we first have to derive what is the expectation and the variance of u and how we can introduce autocorrelation in our model. I have said that for simplicity, we assume that autocorrelation is of the first order. First order autocorrelation is present in our model. If you have this kind of a model, you can use this kind of recursive relationship to find out a general expression for UT. Now, if you continue this recursive process for R periods, this is the general form, right? Now you can use this form to find out the expectation and variance. See, here I have taken the expectation on this general form, which has come out to be 0. So under autocorrelation also expectation of UT is 0. And the variance takes this particular form. sigma E square upon 1 minus rho square, right? So this is what we have. And then what you can do, you can find out the properties, you can verify the properties of the estimators under autocorrelation. So here you have only one estimator, right? Beta is the only estimator. Beta is the only parameter that you want to estimate basically. So for that, I have defined this beta cap auto, and I have shown that this is still an unbiased estimator. As I have told you, under autocorrelation, what were the consequences? The estimators will be consistent, unbiased, but inefficient, right? So these were the consequences. So this is the unbiasedness thing, consistency is holding, and this is the process how you can define the variance, right? This is how you define the variance. This is what we have shown here is that variance of beta cap auto is what the variance we have obtained in under blue and plus some of the additional term. Some extra term is there. You might solve it little further or may not solve it. This term will be a little messy. You will not get any concrete form. So you'll have an additional term which tells you that variance of beta cap auto exceeds the minimum variance, which basically means the estimator is not blue or it is inefficient, right? I hope you got this process. If you have any questions, any doubts, you can let me know in the comment section. And in the next video, I'll be going into the details of Darwin-Watson test. And that will be the last video on autocorrelation. So thank you so much for your time. I hope you like this video. If you do give me a thumbs up and do subscribe to this channel, Economist, and I'll keep on making this useful videos for you. Thank you for your time.